Et nous avons le plaisir aujourd'hui d'avoir du coup Oscar Lopez-Pamies qui nous présentera des travaux récents sur la rupture fragile des élastomères et des problèmes liés à l'incompressibilité, j'imagine, entre autres. Et donc Oscar vient d'arriver à Polytechnique l'année dernière, je pense, que tu as fait le déménagement. Et tu avais fait du coup, tu es revenu à Polytechnique car tu avais fait la thèse à Polytechnique en quelle année?
Oui, c'était 2006.
En 2006 avec le Ponte Castagneda et après donc tu es allé directement à Illinois?
Non, à New York et après Illinois, 2011.
Ok, donc c'est à toi.
Ouais. Well, merci. Corrado, I'm going to speak in English, not to make a mess. And even then, we'll see. Well, thank you very much for the invitation. It's a pleasure to be here. And among other things, because I'm going to talk about something that we have worked on for the past 5 years, and fracture, and this place is a historic place for fracture, right? So I thought it was fitting. And then I intentionally, I have perhaps an aggressive title here. I'm gonna tell you what I mean by that, and then you can then, given the evidence, agree or disagree. Okay, your job. Okay. So this is something that I said I started about 5 years ago, but in earnest, I really started thinking about what led to what I'm going to show you about 12 years ago when I started thinking about cavitation. I don't know if you're familiar with the phenomenon of cavitation in elastomers. At the time, it was not clear what it was. As it turns out, it's nothing but fracture. Okay, so I'll tell you what is driving cavitation. During these 5 years, or actually during this past 12 years, I've been fortunate to collaborate with great colleagues from which we had a great time thinking about these things, and I learned a lot. And I thought of that I needed to single out 3 of them. Aditya Kumar is the former PhD student he did a terrific job. He will start as a professor in Georgia Tech in August. I'm just going to say Gilles Francfort, and that I think suffices. It's been fantastic working with him, and as well with Ravi Chander, more on the experimental side of things. All right. So I thought that I didn't need to have a slide to motivate fracture, especially here, but in general, because fracture is so very pervasive that everybody is familiar with fracture. But then I couldn't help myself, and I had just one slide. And so Benjamin Franklin, okay, a couple of years before he passed away, of course, he lived in Passy for many years, and he had many French friends. And Jean-Baptiste Leroy is actually of d'Alembert, right? So there's a connection there. And then famously, Benjamin Franklin wrote the following. In 1787, the U.S. Constitution was put together. Benjamin Franklin thought that was a magnificent piece of legislation, right? The Constitution. And then he said this, right? This is a great thing, and I expect it to last. But then again, there are only 2 things that are for certain: death and taxes, right? So this is something that everybody uses now, right? There's only 2 things that are for certain: death and taxes. So after 200 years, in hindsight, we can make the following amendment, right? There are only 3 things for certain: death, taxes, and fracture. And this is to anybody. You don't have to be doing mechanics or even science, right? We are surrounded by fracture, and it's truly, truly pervasive, right? So this is, of course, a problem that humankind has been wondering and trying to understand since they were able to observe it, right? So no wonder there has been a lot done in fracture, right? So what I'm going to focus on in this presentation is on the macroscopic view, right? You can look at fracture from lower length scales, but I'm just going to be talking about how fracture looks to us with our eyes, right? Length scales of meter, maybe you can go to microns, but no more than that. All right, so this is the outline of the presentation. So I'm going to essentially say 3 things. In the first part, I'm going to summarize what is that we know experimentally about fracture. We're going to put together the observations or for more than 100 plus years, right? So, and I'm gonna say many things that you already know, but perhaps I'm gonna say them slightly in a more general way and in a more cohesive way, right? So this is what we know from observations, and if we want to explain it, we want to write down equations. We want to put together a theory that explains those observations. And I'm going to say, okay, from here, what is that we need as ingredients to come up with such a theory? I'm going to then present that theory, a theory that I'm going to claim that is complete, quote unquote, based at least on the evidence we have so far. And I'll talk about, some generalities about the theory, and then, of course, some applications, and then some parting thoughts. Okay, so let's get going with what is that we know experimentally, right? What is that we want to model? What is that we want to understand? The first view of fracture, and we're in the right place for that. Love, in his classic book on elasticity that appeared at the end of the 1800s, has a section where he talks about rupture, right? So I'm here recalling that Cauchy came up with stress, right? The concept of stress in 1823, and therefore by the 1850s it was pretty clear, right? You have stress, you have strain. The equations were pretty much clear. What is that we're doing, right? How do we model matter from the continuum? And obviously then people thought about, okay, how within this way of thinking, how do we model fracture? So the first idea on fracture was strength, right? People did these kinds of things, right? You take a piece of rubber or a piece of glass or whatever, you apply tension, it's gonna break. That's an observation that goes back centuries. And then people like postulated that, okay, there is a maximum stress in uniaxial tension at which things will break. That's the idea of strength. And then, other people like Poncelet, Saint-Venant, and others, they said, okay, maybe it's not the stress, but it's the strain. There's a maximum strain. And then they looked at things in tension, and okay, everything works. If you do other loadings, maybe things don't work, right? And so the idea is there, but perhaps not generally. The idea of strength, I'm gonna give you the definition of strength later, but we're already talking about the 1850s, and people were thinking about strength. And things worked for some kind of problems, but obviously they realized if your specimen or your domain of interest has singular geometries, you have notches, or you have regions that are not singular, but things that concentrate stress, like U-notches or something like that, right? Complicated geometries, then this concept didn't work, right? And this was well known, and then Griffith came along, and he said, no, this idea of strength, forget it. What is going on, this is a brilliant statement in his 1921 paper, is that what actually is going on is an energy competition. So inwards, right? We'll talk about the formulation later when we talk about Francfort and Marigo. Inwards, he said, what is going on is I have let's say a body made out of a solid, it deforms, and it's gonna do two things. It can either deform or it can create surface. And there's a competition between deformation and creation of surface. And this creation of surface, in this paper and in other papers he has, he included both nucleation as well as propagation from a pre-existing crack. So in his mind, really what governs fracture is competition between potential energy, deformation energy if you like, and surface energy. And sometimes the material may prefer to create a crack or to propagate a crack. All right, so those were his thoughts. And this is very different from a strength, right? And if you actually do experiments, this is a piece of fancy elastomer with a pre-existing crack, and you apply the force, this works, right? And so there is experimental evidence that this works for this case. But it doesn't work in general, because if you don't have a pre-existing crack, this idea is simply not what happens in reality. So we have the strength as one limit, we have Griffith as the other limit. Of course now, we are in 100 years after, right? 2021. We do have a whole picture experimentally of what happens. So the whole picture is as follows. Your specimen, before you apply loads to it, can nucleate cracks in the bulk. You may have pre-existing cracks in your domain. And of course, you also have boundary points. And these boundary points could be smooth. They could be smooth, but with high gradients. Be not smooth with a corner. And in addition to this, you may have what I'm calling here small cracks. So I'm gonna be precise on what does it mean large and small later, right? But this is really any given specimen, again, from a macroscopic point of view, can look like this, right? That's all you have. You give me the specimen, geometrically speaking, that's what you have. Okay, so what do we know about nucleation in the bulk? Nucleation in the bulk is governed by the strength. Nucleation from large persisting cracks is governed by Griffith. And what happens when you are not in a crack or you're not in the bulk? Well, the experiments indicate that you are in a transition zone. Okay, so not one, not the other, but something, if you like, an interpolation, according to the experiments. And then we have the idea of propagation. Nucleation, right? What we want to do is we want to write equations that will tell us, if I give you a specimen, and arbitrary, and apply loads, arbitrary quasistatically, can you tell me when cracks nucleate, how they propagate, right? I want to have the whole thing written with equations. So we have nucleation, and then we have propagation. All right, so let me define now what is the strength. And then this is just from a macroscopic point of view, this is very important. The definition of strength is the following. If you take your material and you subject it to affine stresses, right? This is a thought experiment, not so easy to do experimentally, but very easy to do in your mind. Therefore, the point-wise, you're going to have a constant stress, right? This is not uniaxial, simple shear compression, a generic stress. At some point, it's going to break. Or not. Maybe it will be infinitely strong in some kind of loading, but at some point, you expect it to break. So this is going to define a surface in stress space, and we denote it by that. So a surface in sigma equal to 0, that's a surface. And people, you know, if you think about the material being isotropic, you expect the strength to be isotropic, so you have a surface that is isotropic and therefore representable in terms of invariance of the stress. And this is the formula for a classic, if you like, a strength surface. It was not derived as a strength surface. It was derived as a yield surface for soils, but you can use it for strength. And people have done experiments in the 70s and in the 80s. People working in ceramics, that's what they did, right? They subjected the specimens to a combination of constant stresses, the best they could. So approximately sigma 3 is 0, and approximately sigma 1, sigma 2 are uniform in the specimen. And they measure things, right? So do these things break, right? And of course, you have a little bit, and actually more than a little bit, of randomness, right? Stochasticity, if you like. But anyway, you come up with, this is a cross-section, right, of experimentally measure strength for titania, and then you go on and they say, okay, how does it look like in 3D? A Drucker-Prager is a cone. Okay, fine. So idea of strength. If I subject my material, right, this is an intrinsic property, like elasticity, to uniform stress, it's going to break at some point. You measure that, you have your surface. That's it, right? One ingredient. Fracture energy, large crack. You go and do experiments, and now I'm going to define what large means. Large means, right, this is a bit tricky because we don't really know yet how to quantify it, but we're simply going to say that if the crack is much larger than the inherent microscopic defects in your domain, this is alumina, you can see here the grains, and you can see pores there, right? It was made some way, so you have defects, right? If your crack is much larger than this length scale, and again, I don't know how to define that, but much larger, then experimentally, this is going to nucleate from this pre-existing large crack according to this formula, right? That is famous now, right? Okay, so symbolically, this is what we observe experimentally. This seems to be true. Okay, so there are experiments for which you can measure GC, right? All right. One more ingredient. This is nucleation from a pre-existing crack. I'll talk about propagation in a second. All right. How about the transition zone? And this is where things experimentally are clear, theoretically not so much. So this is a typical experiment. People have done a lot of experiments with small cracks, right? This is essentially a plate with a crack of initial size indicated here and under tension. And this is the stress, the critical stress at which the crack goes. If the crack is large enough, Griffith will explain everything. If the crack is small enough, it seems to be the strength, but then you have a region that goes from one to the other, right? This is just one example. One example. This is, if you don't with a small crack, you can go with a notch, or you can go with anything you want that concentrates stress locally. And you have two limits and something in between that seems to be an interpolation. All right, so from experiments, what we know is that there is something, that these are limits really, right? When you say I have a uniform stress, okay. Again, theoretically very easy, not so easy experimentally. And this is when you have a big crack. In between, interpolation. Propagation, right? Those things we can do experiments and then we can correlate what I said with experiments. How about fracture propagation? This is a bit more tricky. And even though Griffith wrote it in words, it was Francfort and Marigo actually who wrote the equation, right? I'm going to show you the equation later. How do we describe fracture propagation? So here I'm saying something that it's not so trivial, right? But if I give you the following experiment, that this is what people do in rubber, right? So I come from rubber. Before I did glass, I did rubber. So take a thin sheet, you get a crack that's called the trousers tearing experiment. This was done by Rivlin and Thomas in the 50s. And then what you can do with this experiment is that you can control how the speed at which the crack propagates with the boundary conditions. So the speed of the loading condition, which is applied here, you're applying forces here, right? You take a piece of paper, you tear it. Imagine, you have something that is brittle, elastic. The speed at which the crack propagates quasi-statically is controlled by F, or by the displacements you apply. And there you have propagation, and then this formula seems to work. But this is not so simple, right? What happens if I have paths that are not straight, right? So we're going to come back to a 1998 paper, right? That is essentially, I'm going to call it Griffith, but it's not quite that. It's that written for real. All right, so summing up, what do we know from experimental observations? That there are three things, maybe more, but there are at least three things that one must account for if we hope to have a complete theory of fracture. We need elasticity, and I'm writing things here in finite deformations. Later I'll show you small deformations, right? This applies to rubber as well. Believe it or not, rubber is perhaps the most brittle material on the planet. Okay? Yes, the elasticity is finite, but there's nothing but elasticity and creation of surface. There's nothing really going on other than deformation and creation of surface. But the elasticity is finite, so what? It's the same, right? All right, so three ingredients: the energy, the strength surface, defined as it was defined. You subject it to a constant stress. When does it break? And the critical energy release rate, right? So assuming things are isotropic. All right, for linear elasticity, I'm going to call strain E, and the stress is going to be sigma. All right, a complete theory. And complete, I should have put quote unquote, then we'll see about that. All right, so what is the starting point? How do we build a theory that accounts for all these ingredients? So this is actually how it happened, historically, at least for us. We started with Francfort and Marigo 98. So what is Francfort and Marigo 98? It's Griffith, but formulated mathematically in general, right? And was this that when written in a regularized fashion, so that you can do numerical implementation of the idea, the now famous phase field approach, right, or regularization of fracture. This is essentially, if you like, Griffith in the sense of what he said: competition between elastic energy and surface energy, or fracture surface energy. And this will tell you, well, when fracture nucleates from existing cracks that are large, as well as how fracture propagates. All right, so a couple of things about the original phase field approach to fracture. A lot of work has been done, right? Corrado has done a lot of that work, and this is amazing, right? Fracture propagation is very difficult. And compared with experiments, check. This seems to be what happens in reality, okay? But this original approach, of course, it's incomplete in the sense that it does not account for all the ingredients that I mentioned before. I know that one ingredient is strength. Without strength, and in particular the strength surface, I cannot nucleate in a way that is consistent with experimental observations in a bunch of problems, right? So how do we modify this? As I said, this is our starting point. How do we modify this to account for this third ingredient that is not here, right? Here you have the energy and you have the GC. Before I do that, I thought it was important to talk about something that has been done along the way, that it's been used a lot, but it's still does not address all the observations, right? So the idea, and it goes back to Jean-Jacques and Corrado, is that they realized that somehow, and this is very important, right? So what I'm doing is, this is when we realize that the equations somehow probably are general if we account for a general strength, that are able to account for nucleation somehow, right? But this way, it's, let me tell you, right? I mean, most of you are familiar with this, right? If you choose the 81 regularization, you know, and then you use this function for the degradation, then if you fix epsilon, the regularization parameter, to the tensile strength, then this seems to capture tensile strength correctly in 1D, right? When you do uniaxial tension. So somehow these equations not only give you the right propagation and nucleation from existing crux, but maybe, right, they're able to do more. But okay, if we use this, there is a problem with this. Actually, there are three essential problems. Again, the point of view of complete theory of fracture. So the problem, the first problem is that if you fix epsilon, the regularization parameter, therefore you cannot pass to the limit because it's fixed, then you are giving up having a fracture theory, and then you switch to having a damage theory. And that's, if you want to have a damage theory, it's fine. But I don't like damage theories because I don't understand what damage is. From an experimental observation, you see deformation and you see cracks. So to me, again, this is a personal taste, okay? I feel more comfortable with the notion of a fracture theory, where I am saying I have deformation, I have surface. Sure, the surface is regularized, but it's still a surface, right? So that's one problem, right? That we cannot really view this then as a fracture theory, but as a damage theory. The other problem is obvious. If you only use the tensile strength, this is just one point in the entire strength surface, right? So as I said, from experiments we know that we might have an entire strength surface, not just the point in uniaxial tension. And again, when you fix epsilon, you get actually an entire strength surface that has been fitted to uniaxial tension. That is the formula, and then you can plot the formula and compare with experiments. But again, this is not surprising, right? Because you're calibrating things with tension, but there are other directions that are not calibrated, right? Okay? So, but again, but somehow, this is telling us something very, very important. That the equations are general, right? That somehow you have nucleation in the equations if you put it, right? This is just one calibration. But okay, what if you do a different calibration, right? So this is actually how we realize that maybe we need to deal with this in a different way. So even though it's 3, it's really the first thing that we run it because we were dealing with elastomers. So elastomers are incompressible. So if you look at what happens when you do this theory, when you use this theory in the first quadrant, so this is the strength surface by calibrating things with the uniaxial tension. If you fix everything and the only thing that you change is the bulk modulus of your elasticity, the surface, let me show you cross section, right? Kappa is the bulk modulus. For kappa near mu, things are actually not that bad, right? That's reasonable. But when you start to increase kappa, you realize that the strength surface is doing something that is not physical. It's telling you that when you do hydrostatic tension, which is worse than uniaxial tension, the material gets stronger, right? That it will never break when you make it incompressible, right? And this is essentially because at least for this specific case, you have an energy that is going to zero. If you have a material that becomes incompressible and you apply hydrostatic loading, we know that the energy goes to zero as 1 over kappa. The stress goes to a constant. So when you become incompressible, you have no energy in your system, you only have stress. And that's essentially what is happening here, right, for this type of calibration. Okay, so there are these 3 issues. So, but the idea, you know, I think this kind of result was very telling, or at least very encouraging. Somehow, these equations have nucleation while keeping propagation a la Griffith. So this is the idea. The idea is we're going to change, we're going to use this as a first step, as I said, and we're going to modify. The modification is basically a 2-step modification. We are going to give up, I'm sorry, we have a lot of discussions. We're going to give up our variational view of fracture. We're going to go directly to the Euler-Lagrange equations, and that is what we consider our model. The model is not the variational principle. The model is the equations. These equations are 2 PDEs, right? You're taking variations with respect to the displacement field and with respect to the phase field. In the Euler-Lagrange equation, we are going to modify the driving force that drives nucleation, namely which drives evolution of the phase field. So we take these Euler-Lagrange equations and we go to the one that is for the phase field, that's for the displacement, that's for the phase field. And this is classical except to this, right? We are going to add, this is the right-hand side of the evolution equation for the phase field, we are going to add a driving force there. And why are we doing that? Is because, again, we realize from the original work of fixing epsilon that it is the right-hand side that is controlling nucleation. If you do something to the right-hand side, you're going to affect nucleation. And then, of course, if you do something to the right-hand side, you're going to also affect propagation. So you know, by doing that, perhaps we have completely killed propagation, which is, right, something difficult. So something you want to keep. It is not trivial that a driving force here will bring in the strength that you want while keeping propagation. But it does. So I'm going to show you a couple of examples. All right, so this can be viewed, this is not in vacuum, right? This can be viewed within the context of configurational forces, right? So this is nothing but Newtonian forces driving deformation, configurational forces driving changes in configuration, in this case, the phase field. All right, so this is actually pretty standard. So we have, right, balance of Newtonian forces, balance of configurational forces, V is an order parameter. So this has been done in different contexts of physics and mechanics, not just fracture. So this is not in vacuum. Now the key point here is that in the context of configurational forces, you have what's called the configurational stress. That's the internal configurational force, and CE is the external configurational force. So why are we saying that what we need to add is an external driving force, not internal but external? And then I have a lot of discussions with a lot of people about this, essentially saying that I'm crazy and all. Okay, let me explain. Right, because what is this external driving force? It's the analogous force to the body force in mechanics, right? So think of gravity. Gravity is doing something. CE is exactly B in the context of configurational forces, right? So you say, what do you mean? What is the external agent? What is doing things to the evolution of the configurational, to the phase field, right? So the reason is that if you consider internal forces or even the configurational stress, you cannot possibly be in agreement with experimental observation. That's quite simple, you know. We can look at modifying this, we can look at modifying that, you will not be able to explain anything. So that's why in this framework, again, this is just one way of thinking about the equations, this is an external driving force. All right, the construction of CE. Let's say that we're going to look at this basic problem. The elasticity is isotropic, the strength surface is Drucker-Prager, and this is the formula, and it has 2 material parameters. And you can use whatever you want for those 2 material parameters. Whatever 2 points on the surface, you can pick and calibrate your surface with that. Here I'm choosing tensile strength and compressive strength, but you could choose any other 2 points, right? It's just a 2 parameter type of surface. All right, so how do we now construct a driving force that brings into the equation the strength surface, right, the emitted ingredient, without destroying the good thing about the equation, which is propagation of fracture, which is the difficult thing, right? So this is something that we are not entirely satisfied with it, but we can demonstrate that you can find such a thing, but it's something that still requires some work. So let me tell you the basic idea. The basic idea is the following. The driving force that you choose is of the same functional form as the strength surface, except that you have coefficients that are epsilon dependent. All right, so you give me Drucker-Prager, my driving force is Drucker-Prager, but I have coefficients. And these coefficients have to do something when epsilon goes to 0. Remember that epsilon is a regularization parameter. We want to pass to the limit. We cannot, but ideally we want to pass to the limit, right? Asymptotically, what has to happen with these coefficients is that the equations have to give you that in the when you're applying affine stresses, when the stress is homogeneous in your simple, these coefficients have to behave in a way that you recover exactly the given strength surface. And okay, we know how to write that. And the third guiding principle is that you need to allow for the driving force to be possibly not 0 in the ground state. Even when you are applying nothing, the value of this driving force, you don't have to fix it to 0. And we need this, I'm going to show you now, because you need to espouse, and that's the difficult thing, how do you espouse strength, which is a surface in stress space, right, with GC, which is when you have singularities? How do you marry that, right? We're going to essentially come up with a formula that apparently do that, but again, that is it's not entirely clear yet that we can do it, but again, we don't have something very clean. So this is just an example. If the betas go like this, and there's a parameter here that I'm calling delta epsilon, then we will recover a strength as given, and this parameter is key. This is an epsilon dependent coefficient that needs to be calibrated so that the resulting phase field model maintains the Griffith propagation. If you don't put the right number there for a given epsilon, and you run propagation, you are going to get Griffith-like behavior, but with the wrong GC. So there is something that we need to calibrate, and we can only do it at this point numerically, right? We run the model, and we want to have agreement with Griffith, and that means that for a given epsilon and a given elasticity and everything, there is a unique value of delta, unique computed numerically, that makes this happen, all right? And of course, this is just a choice. We can do something more sophisticated. In fact, we have to deal with epsilons that are not too tiny. All right, so how do we calibrate delta epsilon very quickly? Just I want to give you an idea, is that let's say that you look at a problem for which you know the solution. And there are many, right? The handbook of Tada, there are many. This is just one example, right? A center crack in a plate. We know that the solution, this is not exact, but it's very, very accurate, right? To 0.0% or whatever. You want your theory to give you nucleation from a large crack that agrees with this. And the value that does that for, let's say, titania, the material I showed you before, is this delta epsilon. And this is how delta epsilon behaves as epsilon 0. Okay? This is just a numerical calibration. And for the time being, this is the best we can do. So there's more work to be done here. But the great news is that we can calibrate everything now, and that it seems to work. And I'm going to show you, well, we have done actually many, many comparisons. Everything has checked out. So I'm going to show you just two simple calculations. But summing up, what we have is now a theory, regularized theory of fracture, that accounts for all the 3 basic ingredients that are required from experimental observations, and that by construction, it's going to give you the right nucleation in the bulk, and the right nucleation and propagation from pre-existing cracks. And autonomously, and this we do not understand it, we simply observe it, autonomously, we do not control the transition zone. The theory does the transition by itself in a way that seems to be consistent with experimental observations. So remember what we control, the input is this value and this slope, if you like, right? The rest we don't control. That's the transition zone. Autonomously, these equations, magically, seem to be describing what happens, right? And that, I think, is remarkable. And there's something magic about these equations. All right, so applications. How am I doing? Ten minutes, okay, so perfect. All right, so I'm going to show you, we have done many comparisons with many materials, many geometries, many loading conditions. I'm going to show you two that are very challenging. One is indentation of glass, and this was done by Hertz, in the 1800s, but I'm going to show you experiments by people in the 1980s, right? And then a stretching of poker chip rubber specimens. So going back to the origins of all this, we started this by looking at rubber, and then obviously rubber is elastic. You can take the limit of small deformations. You can look at any linear elastic material you want. So there's a problem here that those of you who know it, a famous problem in elastomers. Okay. So so this is a summary of what we have done so far. We have looked at truly many different materials, right? Things that are essentially incompressible, things that are very compressible, large deformations, small deformations. It doesn't matter, right? I mean, you have elasticity and creation of surface. Things seem to work. That's why. So its final title, it merely suggests that maybe these equations, provide a framework that allows to describe completely fracture. All right, that at least it is what the evidence points to for the time being. All right, so I'm going to talk about these two problems that are actually very challenging, even though they are famous in the sense that they have been done for a long time, but they have not really been explained quantitatively. Anyway, all right, so let's start with a block of glass under a cylindrical indenter, and then we're going to talk about the so-called poker chip experiments. All right, so these experiments were done by Muginot and Mugis in 1885. And these are the dimensions of the glass plate, and this is what they did. Very interesting. So they treated the surface of the glass with different sandpaper, and also with some polishing gels or whatever. So what that does is you create roughness in the specimen, and that means that you create defects, if you like, these inherent defects that are much larger on the surface than in the bulk. Right? Glass can have very tiny defects. That's why it's so very strong. But if you start to mess around with the surface, you start to scratch it, well, you're going to make it weaker, right? So the strength surface is the macroscopic manifestation of the presence of inherent defects in the material. Materials break at a finite value of stress because one of those defects is going to go, right? So this is a macroscopic theory. We are not modeling defects explicitly. We are modeling defects implicitly through their macroscopic manifestation, which is the strength surface. All right, so they looked at a bunch of indenters, and these are the sizes, and they apply, the experiment was driven in displacement with this rate, right, which is quasi-static. And this is what they observed invariably, right? This is a cross-section of what's happening. They saw that they nucleated a crack, which we can call a ring crack, at a given distance of the indenter, and more or less vertical, and after some height, we call it h, it turned into what's called a cone crack, right? So nucleation, propagation. So that's what they saw. And then what I'm going to show you is comparisons of their measurements for a number of these quantities with the theory, right? Theory, we need to calibrate the theory. This is very important. Calibration of the theory means that you need experiments. And believe it or not, there are not so many things you can use to calibrate, right? Elasticity, no problem. They actually did some ultrasound measurements by which they essentially measure very accurately the elastic constants of their, it was a borosilicate glass. So this is the Young's modulus, that's the Poisson's ratio. Strength. This is where we run into trouble. We know that strength is a surface, but experiments are very difficult to do for all in the entire stress space. Basically, you have tension, maybe you have compression, maybe you have shear, but that's it. You don't have much, right? So they did not provide strength values, but they did provide that the roughness, right? They give an estimate of the roughness, which is essentially 1 micron or something like that, on the surface was much larger, right? The defects after scratching the surface were much larger than in the bulk. So this is how we're going to model it. We realized that, okay, if the defects on the surface are very large compared to the bulk, the strength on the surface must be smaller than in the bulk because the defects are larger, right? That's our interpretation of strength, the behavior of defects macroscopically. So so we use Drucker-Prager. Now, is Drucker-Prager a good model for glass? I don't know. You have to do experiments, right? Again, this is a macroscopic theory. You need to calibrate with macroscopic data. We use this, okay, and see what happens. And actually, you will see that it doesn't really matter what we use because of something I'm going to tell you. So Drucker-Prager, heterogeneous on the surface, this value of tensile strength and a large value of compressive strength, this value of tensile strength in the bulk. So, okay, that's our strength. Critical energy release rate, they didn't measure directly. From the cone crack, they came up with an estimate which is, consistent with other measurements of GC for glass, 9 newtons per meter. Now, choice of the regularization length and the corresponding calibration of the coefficient delta epsilon. So remember that we have a delta epsilon in this driving force that needs to be calibrated. Once you have all the data, and once you choose an epsilon you can choose whatever you want, sufficiently small, right? Choose an epsilon, then you need to calibrate delta epsilon. And the calibration is the same thing I told you before, right? Make sure that you agree with Griffith. If you change epsilon, you need to change the delta epsilon, right? You need to you need to calibrate for all epsilon that you use. So this is what we use in the region where we have a smaller strength. We use this value for epsilon, and in the other region we use this value. Why do we use two different values? That's something I haven't told you, but okay, very quickly, okay, for the experts. Yes. 2 epsilon, yes. Okay. So okay, it's the same one. Okay, so that's okay. You're gonna understand it, right? It's a bit technical because this is PDE with epsilon regularization length scale. The PDE cannot see things that are smaller than epsilon, right? So epsilon, if you like, is the smallest length scale that the PDE can see. If you're going to create a crack, it has to be epsilon size. It cannot be smaller. So you can do 2 epsilon or you can do larger. The results won't change, right? But you need at least 2 epsilon to have consistent results. Otherwise, the PDEs will not see that you need to nucleate a crack, right? If you make it too small. So this is essentially because it's regularized, right? Having said is that when we use this theory, the thickness of the phase field crack is not epsilon anymore, right? So we know that essentially it's 2 epsilon or a factor epsilon. It is affected by delta epsilon. So the actual size of the regularized crack that you see in the solution depends both on epsilon and delta epsilon. In fact, it's smaller than epsilon. And the more you increase delta epsilon, the smaller it is. So because we have different strengths in the layer with the abrasion and in the bulk, we wanted to have the same epsilon throughout the entire solution. So that's why if we change the epsilon, we actually change the thickness of the phase field crack when you change delta epsilon. And that's why we have 2 different epsilons, right? It's the reason. Okay. All right. So in the solutions that I'll show you, again, epsilon can make this or you can make it smaller. It doesn't matter. The solution is the same. It's epsilon independent, at least numerically, right? It's really truly independent of epsilon. All right. So let me show you what happens. So this is a contour plot of the phase field. V, right? V1 means no crack, 0 means crack, right? So what we see for this particular case of the indentation size is nucleate very fast. I mean, as fast as we can tell numerically, this is happens instantly. A crack that is at a given distance, right, of the indenter and has some age to it. And as you continue to apply U, remember that this is driven in displacement, right? Then you turn into a cone crack and then you propagate. And that's essentially what happens in all the simulations. Of course, the value at which things happen and the distance and all that changes, right? But I'm going to show you now the comparisons with experiments. Now, I picked this problem because it's actually very challenging for a number of reasons. But one of the reasons is that why is it nucleating there? It's nucleating there because this is the bulk, right? The solution, you have a singularity because of the cylindrical geometry of the punch. But that singularity gives you essentially negative compressive stress. It will never crack there, right? Away from that geometric singularity, the fields are smooth. There is no infinity anywhere. This is nothing but nucleation in the bulk. The fields are not exactly homogeneous, they are heterogeneous. And when you look at that region, you are actually very close. In fact, on the surface, you are exactly here. Right? One of the stresses, the principal stress is 0, and the other two are negative to one another. When you move down from the surface, you have full triaxial fields. On the surface, you have simple shear. So essentially what's happening is that why this is nucleating there is because the stress is hitting the strength surface around shear. So this has nothing to do with tension. This is shear in a macroscopic point of view. Of course, if I put a defect there, maybe it will be tension, right? But this is a macroscopic theory. We do not model defects explicitly. We have a strength that does that. The strength is essentially the macroscopic manifestation of defects. So this nucleates there because of shear strength. So that's why I said before, if you have a, not a Drucker-Prager, but any other thing that has the right shear, then you're in business. You will nucleate properly. And after you nucleate, Griffith takes over. Francfort and Marigo. Okay? And then you can compare with experiments, and it looks good, right? I mean, of course, the experiments have quite a bit of scatter. The blue is the experiment. This is the phase field. This is interesting. If you're interested in buying a car with armor glass, right? This is why glass will not break when somebody shoots at you, right? This is exactly what happens, right? If this is beautiful. So this is the critical force at which you nucleate the ring crack as a function of the size of the indenter. If the indenter is larger and larger and larger, you have to apply huge force, right? So to break a piece of glass, that's why you have these little things in the trains, right? You want to hit it with something that has very, very small area. And then you only need a small force to break it. The problem with a small area is that probably if you use it in the metal, you're going to yield. Yield, you become thicker, and then forget it. So, you know, that's actually interesting. That's why bullets won't go through the glass. Of course, if you have a defect, then you're in trouble, but okay. So this is the numerical, the comparison with the distance at which you have the ring crack nucleated. And then you can compare things that have to do with propagation with the cone crack. This is the diameter as a function of the force, right? You apply displacements, but you can measure the force. And this is the angle, which is pretty much, you know, experimentally, what was it, 22? But with the phase field, you get, you know, something. So it's comparable, right? So, all right. Once you nucleate, Griffith takes over, but you need to nucleate. In this problem, you nucleate because of what happens around shear. All right, so very quickly now, I'll switch to rubber, and then I'll stop. Just to show that, you know, we had glass, now we had rubber. There are these famous experiments, if you're not familiar with the literature in elastomers, that were done by Jan and Lindley in the 50s. They essentially looked at very thin discs of rubber bonded to metal plates, strongly bonded, where the thickness of the rubber was very, very small compared to the diameter. And because rubber is essentially incompressible, right, something is going to happen here. Essentially, when you pull, this is what they did, more or less quasi-statically, a variety of ratios, right, to height. The deformation is really not homogeneous. It's very heterogeneous. And this is what they saw, right? This is what they did. This is what they observed. They were measuring the force as a function of the applied displacement for a number of initial heights. And they always saw the same thing, that the force, I mean, was more or less linear or stiff, if you like. Then there was a plateau, and there was a secondary stiffening. When they stopped the experiment, actually, the pictures I'm going to show you are here. When they stopped the experiment after a while, this plateau, essentially, they connected to the fact that cavities, as they call them, but they're actually cracks, appear within the bulk, right? Here you have a picture of the thinnest specimen, very thin. You have many, many cracks that look more or less as discs. If you go to a bit thicker of a specimen, you do not have many cracks. You only have a few, but the geometry is very different. So this is the midplane, right? So you're looking at the specimen in the midplane from the top. So if you have something that looks like a crack like that, is because the cracks are actually vertical, right? Or possibly that's where they are, vertical, right? All right, so I'm not gonna talk about the calibration, which is not that easy. But again, you go and run the theory, and I'm just gonna show you comparisons of this is the force versus the stretch, right? The global force. And I want to point out that this is 6 times, right? And locally, you even have more stretch. So this is truly very large deformations. So what happens here, according to the theory, this is a zoom region here. It's essentially what seems to be happening in experiments. So quantitatively, things more or less agree. And your movie, what is that you nucleate in the bulk. So this is also nucleation in the bulk, but it's not driven by shear strength. It's driven by hydrostatic strength. So essentially, you're pulling directions, but because of incompressibility, the stress field is essentially hydrostatic, not exactly, but essentially. And at some point, you hit the value of the rubber, then you nucleate. And whether you nucleate more or less, and how many, and if they propagate, you let the theory decide. So this is a picture of the midplane in the undeformed configuration, and this is in the deformed configuration. So we're in the context of finite deformations, right? Things look different in both configurations. So you can see that you have nucleation all over the place. You get many, many, right? This is what we saw in the experiment. And so this is what happens according to the theory. And it seems to be in agreement with experiments. Let me show you now a thicker specimen. Remember, when you make it thicker, you have less number of cracks, and the geometry is very different. This one is very thick. We only see a bump here, which suggests there is only one crack, and that is actually what happens in the experiment. So this is the simulation. Again, this is the midplane, undeformed. This is deformed. You're going to nucleate here in the middle. In the deformed configuration, it's going to look large because it's deformed, right? But it's nothing but a crack. This is actually very interesting. When you pull on a thick specimen, the crack nucleates near one of the boundaries, and it propagates downward. So you're pulling in this direction. The crack goes down, which is counterintuitive. The reason why it goes down is because of incompressibility, right? And again, it's Griffith says that happens, and then you compare what happens in the midsection, and okay. This, to me, looks very convincing. So I think this is very encouraging. So some parting thoughts. All the validation results that we have until this point suggest that this is maybe the law of the land. It's strength plus Griffith view through Francfort and Marigo lens, okay? Not just dW, d lambda, whatever, d gamma, GC, right? The actual thing. This seems to be the law of the land for fracture. Of course, we need to do more things, more validations. We need to understand more. But, I mean, given what we have seen so far for these very different problems, this is very compelling and very encouraging. We are now things that are not elastic. We have a lot of experiments, in particular elastomer, that are viscoelastic. So you now have a system where you have dissipation, not through just creation of surface, but you have dissipation in the bulk through viscous deformation. And we are not there yet, but what we have done so far suggests that this still applies, okay? So these equations are very good equations. Okay, so a couple of thoughts, parting thoughts, and this is homework, right? All right. If we truly think we're doing fracture, we want to pass to the limit as epsilon goes to 0 to end up with a sharp theory of fracture. The numerics suggest that when you go to epsilon very small, you are converging to something. Okay, but that's just numerics. We really want to pass to the limit. We don't know how to do it. If we pass to the limit, I think thing will be clear. How is strength espousing Griffith? And things will become evident if it's possible to pass the limit. But okay, we have a long way to go there. Even from a different perspective, coming from a background of homogenization, I'm not entirely satisfied with this theory. This theory is great to apply whatever, but okay, can we actually look at the problem accounting for the defects explicitly and then passing to the limit? Essentially homogenizing the problem, accounting for defects explicitly, and then coming up with a macroscopic theory as the homogenization limit of a local problem. If we can do that, I don't even know how to describe defects geometrically or constitutive, but let's say you do that, and then you pass to the limit, and then a strength should emerge, right, from that homogenization. But again, these are two, I guess, big open problems, but I think very, very important for us to understand what really is going on, right? And with that, well, I finish, and I thank you for your attention.
Thanks a lot for your very nice talk. So we have time for a few questions. Sure that you will have some.
I would like to come back to the indenter experiment.
Okay.
If you could just show the picture where you see, yes.
Yeah, there.
Or perhaps before.
Before. Okay.
Yes. Yeah.
This one.
Anyway. No, the one where you see the propagation path.
Okay, there.
You say that this is the crack is subjected to shear. It seems to me that this is true if once the crack length is large enough, because it's clear you push on the indenter, so you understand that if you push on the indenter, the crack, which is here, is subjected to that goes loading like this, so the crack tip is loaded in shear. But this is true only if the crack length is sufficient, because at the very beginning, because of the boundary conditions, you can only have tension in the direction of the horizontal direction.
Actually, that's not true.
That's not true.
Okay, so there are solutions. So before people looked at fracture, then all the fields are going to be very difficult. We actually have the elastic solution before fracture, right? This is just an elasticity problem, the classical indentation problem. So it's in the paper by the guys that did the experiment. But before that, it was done on the plane, on the surface, only on the surface, right? Let's call it x30 or whatever you want to call it. You are in exactly simple shear. If you look at the principal stresses, you have sigma minus sigma 0 on the surface. That's the elasticity solution, right? So this is before nothing happens, no nucleation. Have an elastic solution.
In which frame, in which basis, you say sigma minus sigma?
Principal stresses. Principal stresses. That's the solution, right? Principal stresses. I haven't told you what is the orientation of the principal stresses, but the principal stresses, which if your material is isotropic, right, that's the only thing you care about is what are the values of my principal stresses for my surface in a strength, right? So immediately after you move a little bit down, then you have full triaxiality. You have actually high gradients of the elastic fields, right? So it's very complicated. This is it's not exactly a fine stress, right? You have high gradients. Still, they're smooth, right? So what happens again is the theory picks up nucleation there because you are in a region. If you think about stress space, you are in a neighborhood of simple shear. So if I go back to this is Titania, but Okay, just to show you a picture, right? That looks something similar. Let's go back to the data here. We are somewhere right in the 45-degree angle there. So we are here. We are not there. We're not there. We are there, right? So that essentially what this says is, okay, if you are hitting the strength surface, you're hitting it near simple shear, not tension.
Okay, I have to think more about it.
Right, but what's clear what I said, right? That the elastic field, it has been worked out, and you can, in particular, yeah. Okay.
Do you have any other questions?
Do you view your approach as a numerical regularization or as a physical theory? Because it's all based on this Ambrosio Tortorelli thing, which was viewed as a purely numerical way to approximate free boundary problems. But now you are using the word configurational forces. It starts to look like a physical theory. So what is...
Okay, that's a tough question. I mean, I call it a theory in the sense that, let's put the equations. Let's put the equation there, at least for linear elasticity. Yeah, so exactly, right? Within the context of configurational forces, this is a theory in its own right. And if you look at it from a variational point of view, regularized, it's not the same, right? So you can view, I guess the answer is depends, right? Personally, I view it as a theory that it's implementable numerically, PDE based. But to me, this is a theory because it's essentially epsilon independent, right? So we have, and again, this is proof of nothing, right? But numerically, we see that it's insensitive to epsilon. So provided epsilon is sufficiently small, these equations will always give you the same solution, right? It's not gonna, right? So from that point of view, I think there is truth in these equations. But at the same time, I have to be honest, so long as we are not able to pass to the limit of epsilon goes to 0, to the sharp limit, because I want to think about this as a fracture theory, then it's not entirely satisfying, right? Because there's something hidden here that we don't quite understand yet. That it works. That is remarkable that it works, okay? This is fantastic, but okay, it's not entirely clear what that is doing, and I think it will only become clear when we have a sharp theory. There will have deformation, surface, and then it will be obvious, right? It will be not Ambrosio Tortorelli anymore, right? It will be sharp theory.
So do you think that finite epsilon E doesn't make any physical sense?
Okay, no. It's I don't believe in damage. I believe in fracture, right? But again, that's just my opinion, right? Because this is what you see in the experiment, right? You see the surface. I don't see the damage. I see the surface, right?
Okay, thanks a lot. I think we have more questions, but I think it's time to stop.
I'm perfectly comfortable being no variational. So you see, our initial conditions are very different. So you feel uncomfortable, but I never, I don't have feelings for variational. If you can do it, you can do it. That's great because you gain things. But I can give you. You see, my background is more elastomers, right? We're gonna have dissipation, viscoelasticity, whatever. Right. So again, I mean, to me, I think that's why I call it the primal model. To me, what is the equations are balance equations. I believe that there are equations that describe how things behave, right? So the divergence of stress, the divergence of configurational forces. To me, I take those as principles, and then you just need constitutive input, right? Those apply to everything. What is your constitutive part, right? So from that point of view, I don't feel uncomfortable, but I understand if you do. Okay, I can only tell you that. Okay, you're welcome to try to do it variationally, but you will not be able to address things later on, right? That are not elastic, right?
Okay.
Yeah. Okay.
My question is about
It doesn't matter. As I said, it's just an example. Okay, so this is actually okay. So let me emphasize this. It is completely physical. I tell you why. Because in compression you can put whatever number you want, right? You have to be careful that because you have Drucker-Prager, again, you don't have to have Drucker-Prager. You can have whatever you want, right? But this is just a simple way to do it. Nothing will happen here because the compressive strength is so strong, right? Now, about the tensile strength, we actually don't know what the tensile strength is, right? Because how do you do a tensile strength on something that has been abraded? We calibrate it. To me, this is not unreasonable. The tensile strength here, it doesn't matter because it nucleates on the surface anyway. You know, I can put whatever I want here, it will work. So this is completely physical. The only thing that it is truly calibrated is the shear strength given by this combination of values that we put in there, right, to have agreement with experiments in a Drucker-Prager. But as I said, I can use whatever other thing you want. You can make it work, okay? You just have to calibrate it differently. But the calibration is done so that you get nucleation when you need it, and that is controlled by shear strength, and this is what gives you the right shear strength. And the value that emerges is not unreasonable. Actually, they don't. Actually, they don't. No, they don't. So what they do, that's a good point. So before, actually, that's the paper that motivated us to look at this. What they did was to not use epsilon fitted to the uniaxial tensile strength. They actually control the stresses. I guess they didn't realize, at least it's not clear from what they did. They didn't control the strains, they control the stresses. And even then, they cannot deal with parts of this experiment. So they only have they can only compare with some of them, not the others. So it is in complete comparison. It's not a complete comparison, and it's not the original. It's modified because the original will not give you the right thing. Yeah.
Okay.
Right.
Propose to stop here. Thanks a lot.
Okay. Thanks.